Hello, everyone. I'm Jiang Zhu, a project scientist at the Paleo and the Polar Climate section at NCAR. Today, I'm going to give you a very brief introduction about water isotope modeling with CESM. So first, a very basic question, what are water isotopes? We know that for regular water, the molecular form is H2-16O. So for the oxygen here, we have 8 protons and 8 neutrons. And the H2-16O is not the only molecular form for water. We also have H2-18O. So the oxygen here has 10 neutrons. So as a result, you see that the molecular mass is higher, 20 against 18. This difference in the molecular mass has implications on the physical and chemical properties. Heavier water has slightly higher density, melting and boiling temperature, as well as viscosity. Because the chemical bonds are stronger, so they are harder to break. Therefore, the heavier water has slightly lower chemical reaction rates. Because of these differences in physical and chemical properties, fractionation will occur during physical, chemical, and biological processes. What are those? Take the evaporation as an example. So the heavier water are harder to evaporate. So during this evaporation process, the vapor will have relatively less H2-18O than the liquid. So that's the fractionation. Another basic concept is the delta notation. So because the natural abundance for heavier isotope, for example, the H2-18O here against the lighter isotope is very small. So the H2-18O against H2-16O is 1 to 500. So this small amount is really hard to measure in the lab. So that's why people use this delta notation. So you always compare your sample against some standard. So here, if relative to the standard, your sample has more heavy isotope, so more 18O, then you will end up with a positive delta value. So relative to the standard, if your sample has less heavy isotope, 18O, then you will end up with a negative delta 18O. So for water, people use the V small as a standard. For carbonate, VPDB is used. The figure on the right here shows typical delta 18O values in the hydrological cycle. So at the surface ocean, the values range from 0 to -2 per mil. Evaporation is harder to do for heavy isotope. As a result, the vapor clouds, they have relatively less H2-18O, so the delta value is more negative. And the condensation and precipitation are easier for the heavy isotopes. As a result of these run-out events, the vapor and the clouds, they get progressively lighter and lighter during the movement of the air mass. When the precipitation and snow occurs over polar region, so you see that it's very light, and in the end, the snow and ice at the polar region has a delta 18O around 30 to 50 per mil. You may wonder, why should we care about water isotopes? Because they are paleo thermometers. The left here shows the carbonate of water oxygen isotope thermometer. So here you measure the delta 18O in calcium shells of foraminifera. And assume you know the delta 18O signature of the seawater, then you can plug in this equation to calculate the water temperature when the foraminifera lived. The physical basis for this thermometer is the temperature-dependent reaction rates. So this isotope exchange reaction. And you can calibrate this thermometer in your lab. And you see that a very nice relationship between temperature and the delta 18O. In addition, you can also use ice core to reconstruct past temperature. So the equation is listed here. You see that alpha is at the center of the thermometer. So you measure the delta 18O in seawater, in the ice cores, which is thought to reflect the past snowfall. Then you can calculate the temperature here. The theoretical basis is the Rayleigh fractionation, so heavy water condense more easily, and it's calibrated against the present day climate. You see that maybe the alpha differ a little bit for different regions, and the people are still debating about the details about the alpha. How does the alpha vary with climate change? In addition to temperature, you can also reconstruct rainfall using water isotopes based on the so-called amount effect. Here, this figure x-axis is the tropical precipitation amount. Y-axis is the delta 18O in the precipitation. You see a very nice negative correlation. So the higher the rainfall amount, the lower the delta 18O value. Here, this slide gives you 3 time series of the delta 18O in different archives, just to show you how we can make use of those records. The top shows the delta 18O in the benthic foraminifer calcium shells, so they live in the deep ocean. And you see this large variation, and the period is roughly 100,000 years. So the interpretation is that they reflect the glacial interglacial cycle. So starting from the last interglacial, as the climate gets colder and colder, you see that this will make the carbonate value increase. As the climate gets colder, we also have the ice sheets build up over high latitudes. So the ice sheets will trap light water. As a result, the delta 18O of seawater will also increase. This is another contributor to this increase in delta 18O of carbonate. So in summary, this variation, this reflects increase in decrease changes in temperature and also in the ice volume effect. The middle panel shows the delta 18O in ice core. So you can choose your favorite alpha value and to estimate the temperature based on that. You can see a coherent glacial interglacial variation. And the bottom panel shows the delta 18O in the Speleosome Chinese cave records. And the interpretation is that high values reflect stronger monsoon because the delta 18O in the Speleosome is thought to reflect the delta 18O of rainfall. Therefore, based on this amount effect, and take that as the face value, you can infer past the monsoon change. Hopefully you can see that those records are really powerful, giving us this variation and idea about past climate change. And you can see that there's very nice correspondence about the variations at millennial timescales. Those are really interesting topic to study. However, hopefully you can also see that there are a lot of assumptions involved. For example, we basically don't have a good idea about the delta 18O of seawater. And here the calibration is against the present day observation. And we don't know how well it will work for past climate change. And here you have make assumptions about this amount effect. And we don't have a good handle on the physical mechanism for that, and also how does that vary with climate change. Those questions motivated us to develop this isotope-enabled community Earth system model, so CESM. The goal is to divide this dynamic model to provide a physically consistent simulation of water isotopes in the Earth system. Hopefully, we can use this tool to better interpret the isotope records, and which this tool also enables us to direct synthesis of the model and the data information. So ICSM code is publicly available here via GitHub, and the code is not yet available for CESM2. So there are still work need to be done. And if you are interested, you can check out this paper published in JAMS. So here I want to very briefly show you how ICSM works. So we know that in CSM, we have a comprehensive description of the hydrological cycle, so the H2 water cycle. It has a complete suite of physical processes listed here. For ICSM, it's actually quite simple. We, in addition to this regular water cycle, we replicate that to create this H2 water cycle. It's exactly the same, so has exactly the same physics, except when phase changes, we consider the fractionation. Then that's it. So in the next few minutes, I want to show you an application. So the question we ask is a simple one. How cold was the last glacial maximum? So the LGM occurred roughly 20,000 years ago, and the climate is colder because lower CO2. And we have ice sheets built up over the high latitudes, which will trap light water. As a result, the mean ocean water delta 18O will be higher. And because the differences in thermodynamics and ocean atmosphere circulations, the delta 18O of seawater should also be different from the present day value. The figure on the right shows the LGM sea surface temperature proxy. You see that now we have close to 1,000 records. More than 60 of them are delta 18O records. So this tells you how important water isotope is in the paleoclimatology. So those are delta 18O in calcium shells, so the delta 18O carbonate. In order to translate that to temperature, you need information about delta 18O of seawater. This is largely unknown. That's where the ICSM comes to the rescue. So with the isotope-enabled CSM, we can perform LGM simulation, which provides us sea surface temperature and the delta 18O of seawater. Then we can directly calculate delta 18O carbonate. Now you see that the model and the data, they speak the same language, delta 18O carbonate. Based on that, you can build a data simulation framework to formally combine the information in the proxy data and the dynamics in the model, which allows us not only to reconstruct sea surface temperature, but also surface air temperature and precipitation change. So in this study, we estimated the LGM global cooling to be around 6 degrees C with this uncertainty range. This is a major advancement over the large range in the IPCC report a few years ago. You may wonder, why should we care about an ice age climate? So LGM can be used to inform the equilibrium climate sensitivity. So ECS measures the global temperature increase due to a doubling of the atmospheric CO2 concentration. So it's the Earth's system response boiled down into one single metric. In that sense, it's probably one of the most important metrics in climate science. The figure on the right shows the ECS in different versions of CESM models. The x-axis is the simulated LGM global cooling in each model. And you see a very nice correspondence between the two. In the case of CESM2, its ECS is above 5. It's much higher than any previous CESM models. The critical question is whether this high ECS is realistic. This is not easy to answer because CESM2 matches the present day observation much better than the previous generation of models. However, it's really straightforward if you use a paleoclimate perspective. So if you recall our proxy data reconstructed LGM global cooling, so after 6 degrees C, and you compare, you see that the CESM2 value is too large, meaning that the model is too sensitive to external forcing. Therefore, the ECS is very likely to be unrealistic. So a summary, water isotopes are paleothermometers and rain gauge, but by no means they are perfect. That's why we need a dynamical model to help us to better interpret those delta 18O records. And the model, of course, provides us a physically consistent simulation of water isotopes in the Earth system model, and enables us to directly synthesize information from model and data. And hopefully the idea is to get a better mechanistic understanding of past and future climate change. And CESM can also be used to study present day climate. If you are interested, you can check out this interesting commentary. That's it. Thank you for your attention. If you have questions, please email me.